Okay, let us pick off where we left off. So we're going to look at calculating the shear stresses now. And first we're going to look at the distribution of shearing stresses in beams. Here's some quick criteria. Provided that the thickness of the centroid axis is not greater than some other axis, the maximum shear stress will occur at the centroid. This is opposite to where the shear or where to direct stress due to bending was. There was nothing happening at the centroid for bending in the previous chapter due to normal stresses. For shear stress, it's the opposite. There's nothing at the edges, and it's a maximum at the centroid. So if you are going to calculate the maximum, it's only important to do it at the centroid. Here's a diagram explaining that. The upper left-hand corner is a long, thin rectangular beam. In the right-hand side of that beam, in the blue, it plots the stresses along the axis. You'll see that the maximum occurs in the middle, at the neutral axis. For normal bending, the stress would be 0 there, and highest at the end. This is the opposite. It goes down to 0 and goes up to the maximum. Here's a few other shapes. In the upper left-hand corner is a T shape. Notice that the maximum again is at the neutral axis. Notice that at the flange and the top, the stress is really low, and then right where they intersect, it jumps up. But then there's a little bit of maximum here at the end. And then over to the right, there's a I-shaped beam. Not much shear stress in the flange, and then it jumps up to something maximum in the web. And then at the bottom, there's a plus sign shape where it jumps up to right at the intersection where the vertical meets the horizontal, and there's a maximum there. Notice that for all of these, at the intersection of all the different pieces, the webs and the flanges, the shear stress is huge. So like I said in the first part of this lecture, the concern for these types of beams is where they're connected to. There's a huge amount of shear stress there, so they can easily delaminate or come apart into multiple sections. So let's work on calculating the shear stress in a beam. This is the same rectangular beam we worked on before where we determined Q, but now we're going to do this example. Let's remind ourselves what the equation for shear stress is, which I'm just going to grab from the earlier portions of the slide. It's right here. It's this guy. So I'm just going to copy this guy and work here in PowerPoint. That might be easier. So tau is equal to just VQ over IT. So we know V is maximum shear force of 250 kilonewtons. Q we previously calculated. It was equal to the 500,000 millimeters to the third. But I don't want to work in millimeters. I want to work in meters because I'm going to get stressed and I don't want that to work with the conversion. So converting 500 millimeters to the third to meters to the third gives us 5 times 10 to the negative fourth. That is meters to the third. So I pre-converted that for us. It's the same problem from before, which we previously calculated the Q. I'm just converting it to meters. Now the next thing for us to calculate is the moment of inertia about this guy, which we haven't previously calculated yet. The moment of inertia, if we recall, for a rectangular, I is equal to the base height cubed over 12. And if we do that, we just plug all this stuff in meters. The base is the 100 millimeters. 100 millimeters to meters is just 0.1 meter. The height is 200 millimeters. Converting that into meters is 0.2 meters. That needs to be to the third power. So I'll raise this to the third and divide that all by 12. Not that to the 12, all of this to the 12. I do that and I'll get 6.67 times 10 to the negative fifth power. Moment of inertias are in meters, or in lengths to the fourth. We're dealing with meters, so we're in meters to the fourth. Great. Now we could calculate tau. We have everything already. We could calculate tau. We know the thickness. That's easy, so I don't need to write that. So tau, I'm just going to do capital T. I don't have that symbol readily available. So T is equal to VQ over IT. and we know this information. V is 250 kilonewtons. It's fine leaving it in kilonewtons. Q is the 5 times 10 to the negative fourth. Let me make this bigger for us. 10 to the negative fourth power. That's in meters to the third. All that is divided by the I, which we just calculated, which is 6.67 times 10 to the negative fifth meters to the fourth. And that's multiplied by the thickness. The thickness is this base right here, which also needs to be in consistent units of millimeters, which is 0.1 meter. I do that, all that math right there, and it gives me 18,740. Now what are our units? We will get kilonewtons over meters squared after everything cancels out. Kilonewtons over meters squared is a kilopascal. So the stress due to this section is 18,740 kilopascals. And that's how you solve these guys. If you figure out the Q, which we did from before, then you figure out the I, and then just plug everything into the equation. Okay, now we'll move on to the regular lecture. Now there's something cool about these problems, is because for regular shapes like a rectangle and a circle, Q is just some simple formula, AP times Y bar, and that's relatively easy to calculate. And then the stress is just the VQ over IT. If we put all those things into just variables like the height and the width, then everything can just simplify and stuff crosses out. And for a simple rectangular shape, we can estimate that within plus or minus 5% accuracy by just doing 3 times the shear divided by 2 times the area. And then for a circular shape, tau would be 4 times V divided by 3 times the area. So using these equations, we only really need to calculate the area. We don't need to calculate I. We don't need to calculate Q. So that's super cool. You might be asking yourself, okay, well then why did we learn Q before this? Well, what if your shape isn't rectangular? Or what if it's not circular? What if it's an I shape? Or what if it's a hollow shape? Well, the first part of that answer is, well, there's cool equations for those guys too. A hollow, thin-walled tubular shape is 2 times V divided by A. A thin web shape like the I shape we looked at before is just V divided by the thickness times the height. Well, what if it's not these 4 shapes? Well, I don't have another slide with quick equations. So if it's like a triangular shape or a square shape with a circular hole off into the center or a trapezoidal shape or anything out of the ordinary, you will have to calculate Q. And we'll see that in our example problems and possibly in homework and maybe in exams we'll have to calculate Q. But if it's one of these 4 shapes, rectangular shape, circular shape, hollow thin wall shape, or a thin web shape, you can estimate the shear stress to a pretty close accuracy by just getting V and divided by the area or sometimes using the thickness. That's it. So let's see if this works. Here's an example of a circular section. I want to know what the maximum shear stress is that would occur in this shaft. It's 50 millimeters in diameter, which is approximately 2 inches, and it has a vertical shearing force of 110 kilonewtons. Well, it's circular, so if you use this equation on the right, 4 times V divided by 3A. Well, let's just get that stuff. So the equation for this guy is tau is equal to, like I just said, 4 times V divided by 3 times the area. Well, let's just get that stuff. We know what the area of a circle is equal to pi times d squared over 4. Cool, let's just plug that stuff in there. Pi, the diameter is 50 millimeters. Well, we can just leave this as 50 millimeters for now. That's raised to the second power. That divided by 4, if I do that math, it's 1,963.5 millimeters squared. Cool, we have the area. We have V, V's up here, 110 kilonewtons. Cool, well let's just plug that stuff into the calculator. Tau is equal to 4 times the 110 kilonewtons. Well, let's use that trick that we did a few months back where we work in newtons and millimeters, and so I'm going to put this into 100,000 newtons. That's going to be divided by three times this area I just calculated in millimeters, 1,963.5 millimeters squared. I plug this straight into the calculator. The calculator is going to pop out 74.7. Well, what units? If we do the trick of working in newtons and millimeters squared, it's going to be megapascals. And that's it. We use that simple formula, 4V times divided by 3A. We didn't have to do the Q because it all simplifies out and reduces down to this simple formula. That's the answer for this circle problem. Then if we go back to the regular lecture, we move on and we talk about designing for shear. When you design for shear, this depends on the material. So just like last week, when we talked about design and we figured out the design stress based off of the design formula, we got a number, and then we compared that to tables of different materials, and that number had to be bigger or as close to possible as that value. We would do the same thing here. There's no examples here for it because it's the same exact process. We just get the tau value like we just did here, 74.7. Depending on the type of loading, whether it's static or repeated, we multiply it by 8 or 4 or whatever that value is from the table, and then look up a value in tables for different materials and choose something higher than that value. The next thing is shear flow. Like I said at the beginning of the lecture, shear flow is useful for built-up sections where you want to know what the shear is through the section and how it's flowing through the section. It's abbreviated as Q, and the units for this guy is force per unit length. And it's simply the measure of how much shear force must be resisted at a particular section. So let's do a quick example for that. And we want to do the shear flow for this section that has a maximum shear force of 100 kips. Okay, I'm going to go over here and work in text box. So basically, the equation for shear flow is little q is equal to tau, which I'm going to write capital T, times the thickness. That's it. And we know from the previous slides that for a thin wall section, I'll show you right here, thin webbed section, tau is equal to V divided by TH. So I could come over here and just use that simple formula. Tau is equal to V divided by the thickness times the height. And I could just plug everything in. If I know what that is, V is the 100 kips divided by the thickness. Now what thickness? Okay, that's maybe the tricky part. Maybe it's the 6 inches for the web, or for the flange here, or the 2 inches there. Well, where is shear maximum? Earlier I said it's in the middle right here where the neutral axis is. So it must be that thickness, which is 1.5 inches. Now that needs to be multiplied by the height. Well, what height? 10 inches? 2 inches? Well, remember where the maximum shear stress is. It's on the web and it goes down to basically nothing on the flanges. So it should be this distance from here to here, the web, which is 6 inches. And I plug all this in, I get 11.11 kips per square inch. Okay, well what is Q? Q, the shear flow, is that value, 11.11 KSI, times that thickness, the same thickness that we're interested in, of 1.5 inches. So I theoretically didn't need to multiply this by the 1.5 because it would have canceled out. But what if I want to know what the shear flow is up here? Then the thickness would be 6, or at any different spot. But if we're still looking at the shear flow at the maximum in the middle, we just multiply these guys out, and we get 16.6. And what would our units be? It would be force per length. Force per area would be force per length. So kips per inch are flowing through this section at that particular location. Cool. That ends this lecture that would normally occur on Tuesday, where I introduce the topic and how to work it. I'm going to make separate videos for other additional examples. And that's it for this lecture.